We are back in Turing Complete, and you obviously notice I've got a webcam now. I've also tweaked some audio settings, so it should sound a lot better. Let me know what you think of the audio and video in the comments below. Where we last left off, we had just completed the arithmetic and the memory section, and we are moving on to the CPU architecture. At the end of this section, we should have a working computer, so that's very exciting. To get started, let's start on this arithmetic engine level. Add, addition, and subtraction to your circuit. We have our instructions here, 0 is an OR, 1 is an AND, etc. And oh, it looks like we are starting with the previous solution that we had generated for the logic engine level. So now we need to add in a couple more instructions. We need to add in, we had OR, NOR, NAND, and, so we need to add addition and subtraction. Let's get started here. Let's see what the codes are. So that's an addition and that's a subtraction if we have bits 2 and 0 turned on. If it's just bit 2, that's addition. If it's bit 2 and 0, that's subtraction. All right, this is getting more complex, and as always, I can't move these red components. They've started locking those off, so we can't move them anymore. This was kind of messy last time. Let me just try and clean this up a little bit. I've reorganized this a little bit, and last time we only had 2 bits, so we only needed 2 levels of multiplexers to select all the possible instruction codes that we could give it. This time we're going to need to add in a new multiplexer because we have a whole 2 new instructions we have to be able to choose between. So that's going to complicate things a little bit, but before we get there, let's start by getting our addition and subtraction. And this should be very straightforward here. In our math section, we have addition. So we should be able to add the 2. So let's take our input 1 and our input 2, and let's just wire these up right here. So the output of this is going to be our add. Let me just label that. And then we also need subtraction. So how do we do subtraction? Because we don't have a subtraction logic. So what we're going to have to do is add the negative value of one of the inputs here. Now subtraction, we could subtract one from the other. I think it's going to be subtracting this value from this one. So we'll just set up a negate right here, and we're going to need another adder. Let's put another adder in, and we're probably going to have to offset these. Let's put that in there. This will connect to the second input, and then the first input will go right there. So now we have, this should be a subtraction right here because we're adding the negative version of the second input. Like if I were to take, let's try it with a few numbers and just see what happens. If I've got 3 and 1, we have the value 4 coming out of this add branch, and we have the value 2 coming out of this. So that looks right to me. So we have our addition and subtraction. Now we just need to add those as selections for our output. So the add operation happens when the bit 4 is high and all of the other bits are low. So we're gonna have to figure out how to do that. We're gonna need, first of all, let's go ahead and get another multiplexer here, an 8-bit mux. This is gonna choose between a couple different values here. We need to move these back a little bit and make some space. Okay, let's add in this other multiplexer here. We're gonna be selecting between all those other values and the output of our addition and subtraction here. Now we need, I think we're gonna need one more mux because we have to choose between the addition or the subtraction based on bit 1. Okay, so what I've added here is a new multiplexer right here, and I've added a new one right here. So first of all, we have a multiplexer that's selecting between the add and the subtract. Oh, it looks like I lost my label. Let me add that back in. So we have this blue wire here is our add, and this one right here is our subtract. That's going through to this multiplexer right here. And what is selecting this is bit 1, because when bit 1 is negative, we're going to choose the well, as long as bit 4 is toggled. We'll get there in a second. If bit 1 is negative, we're going to choose the addition. If bit 4 is positive, we're going to choose the subtraction. So that chooses between the addition and subtraction based on the value of bit 1 here. And then we have this new multiplexer right here that's choosing between add or subtract and all the other operations that we figured out last episode, the and, nan, nor, and or. So that's based on bit 4. So if bit 4 is toggled on, then we're going to take the output of this mux and pass it through. If bit 4 is toggled off, then we take the output of this mux. So now if I hook this up, let's test a couple values. We've got 3 and 1 here. Right now it's ORing the bits together. We get a output of 252. NAND is going to give us 254. We got NOR, OR, add is 4, and sub is 2. So let's test that out. Ooh, looks like I've got something wrong here. Let me do a bit of debugging for a second. Oh, it looks like this got disconnected when I was moving things around. Let me reconnect this real fast. Okay, there we go. This has unlocked a component factory entry. Open the component factory by clicking on this button in the upper left bar. This allows you to create your own components. The logic you place determines the behavior of the custom component, and the layout determines the shape. Oh, okay, this is really awesome. So we can create custom components and then reuse those later, is what it looks like to me. That's great. Let's keep going. And here's our component factory. Welcome to the component factory. The circuits you create in here will be usable as components in architectures. The circuitry you create defines the behavior of the component, and the layout defines its shape. Components can be added, renamed, or deleted. Since this level is a tool and not a challenge, you can go to the level map and continue on when you want. Okay, so this saves my solution, and it gives me a preview of what the component will look like based on how many inputs and outputs I have. And it looks like we can do all sorts of stuff. I'm going to leave this alone for now, and then we'll come back to this when we need it. Let's go on to the registers level. Time to create your master project, implementing the Overture computer architecture. This will be an actual Turing Complete machine, a true computer in every way. And that's what we have to do in order to not get eaten by this guy, apparently. I've locked the red components of this level in place since you always make a mess and don't leave enough space. The mess you make from now on is saved between levels, so you no longer get to start fresh each level. Okay, so it's going to be a lot more important to make sure that our designs are compact and organized. Otherwise, it's going to get really confusing later on. In this level, you need to create a circuit which can copy from a source to a destination. The instruction byte in this level determines the source and the destination. Bits 1, 2, and 3 give the destination. 4, 5, and 6 give the source. Source and destination can be one of 6 registers. Registers 0 to 5 respectively. Additionally, this map has a dedicated input component, which can be the source, and an output component, which can be the destination. These are the bit patterns for each source and destination. And to get a more intuitive understanding of the requirements, click the instruction icon in the upper left corner. Create the schematic that matches the code specifications. Okay, so we have, it looks like here are our 6 registers that we're going to be copying back and forth from. Here's the input, there's the output, and here is the instruction word input. And it said I could get some more instructions here. Instructions, click to toggle the bits. Okay, it looks like this is simulating the instruction word, and I'm not sure what these 2 bits are for. I don't think those are used. But this is specifying which register we're going to copy from and copy to. So these bottom 3 bits are going to be the destination, and these upper 3 bits are going to be the source. Okay, so we've got these 6 registers, and let's just start by thinking about how are we going to select between the source and the destination here. And usually when we think about selection, we're thinking about multiplexers toggling between 2 different values. Now this would be a lot of levels of multiplexers, but I think we're going to need it. Actually, let's look at this 3-bit decoder here. This may end up being the ticket. If we were to split this up into the relevant bits here, we could pass these through to a decoder. Bits 1, 2, and 4 are going to be the destination registers. So that's going to determine which destination it's going to go to here. So depending on the status of these bits will tell us where we're outputting to. And then if we get another decoder, this will be our source decoder here. So now we take the next 3 bits, and this specifies which source we're going to pull from. Okay, I've gone ahead and connected up this decoder right here into the load input of these registers. And so that's essentially going to select which of these registers is going to output to a wire here. And remember, we can, if it's got this gray output pin, then we can actually connect all of these up together, because the assumption is that you're not going to have multiple of them outputting at the same time. So this is going to be our, we can think of this as our output bus. I'm going to call this output here. And whichever of these registers has their load pin set to high is going to be the one that's outputting to this bus. So we can see that based on which output register we have selected, that's letting the register output onto this bus. So we can see the values coming from register 0, 1, 2, 3, 4, or register 3 right here, and it's outputting onto this bus here. If it's register 1, then this is the one that's going to be writing to our output bus. Now we just need to connect up the inputs. So that's our source register sorted out. Now we need to figure out our destination register. So this destination register should be pretty similar. All we should need to do is use this decoder to do the same thing, connect up to these save values here. So we're going to be selecting which register we're actually going to be saving to. Okay, now I've got these hooked up. For example, R3, R1, if we remember how this works here, if we had R3, R1, that means we're going to copy from register 3 to register 1. So we see that register 3 right here is the one that's outputting a value. So it's copying from this register, and it will copy to register 1. Now here's register 1, and you can see that its save pin is set to high now. So lastly, we need to connect up the output. And this output bus here, we can just connect it into the save value for each of these registers. That'll go right into that bottom pin. So we should just be able to take this and connect it up to each of these registers here on the bus. Okay, so now we've figured out all of the register to register copying, but we also have this input node and this output node here. And these are gonna act as almost, you can imagine as if there was an additional register, but we need to be able to copy from the input and copy out to the output. If we look at the instructions for the level, we'll see that this pattern here, value 6, corresponds to this input node down here. So if this decoder right here, if it was using this value, if it decodes to here, then it should use the input. For example, right here, if these 2 bits are set high, it's going to use the input. If these 2 bits are set high, it'll use the output. So all we should have to do is really connect these input and outputs up, just like how we connected these registers up using these decoders. What makes this just a tad more challenging, however, is that we now have to select between a value from this bus or one of these input values for what gets passed in. So we're going to have to add a selection between the 2 of those. So we will need a multiplexer in here as well. We'll get our 8-bit mux. And for each of these inputs, it actually needs to be the output of this multiplexer. And this multiplexer is going to have the output bus and this input value here that it's selecting between. So give me 1 second and let me hook all that up. Okay, so I've hooked up our output bus and our input into this multiplexer. And so whichever one of these we're going to copy through to the register is going to be this save value that actually gets saved into these registers. But now we need to select whether or not to use this multiplexer, and that's going to be the output of this decoder. If we take that 6th value here for this copy from decoder, this will let us select what we're going to be copying from. So if we want to copy from the input here, now let's go ahead and change this input value to like 7. We need to, oh, I've got this mixed up actually. Let me switch the ordering of this input and this copy from register value here. Now I'm having some issues. I don't really know why this level input is not actually inputting. That's kind of confusing to me. I'm gonna try and figure out what's going on here, because it's not actually putting the value out. So we will also need to hook up a output enable. Maybe it's throwing me an error because there's no output. Let me try hooking up the output real fast and see if that helps us. And essentially all we're going to do here is connect up this multiplexer to this output. This decoder here is going to toggle between the two different inputs here. We're going to have the save value coming through. Actually, we might just do a bit switch, because that should just toggle whether or not to pass the value through. So this is going to pass through to here, but only if this is selected, and then we'll take that save value and pass it through. So whatever is designated to be saved will get passed through to this output here, only if the decoder is set to use the output. Otherwise it won't pass any value through. I'm still not sure why this 63 isn't coming out of here. I thought it might be this enable right here, but I could take an always on and it's still having an issue. It's not passing the 63 out. I know it's not this multiplexer, because even if I deselect this multiplexer here, it's not changing what's passing through. Actually, I think we don't need the switch. We might just need to hook up this output enable to this selector here. Let's try that. Okay, input should only be enabled when reading from input. Oh, okay, so it just wants, if I take this signal and pass it down here to the input, let's connect that up like that. So it should only, well, let me make that a little cleaner. It should only enable the input if it's actually selecting from the input. Okay, so now that seems to be working. Let's run it and see if we're good. Okay, there we go. Registers complete. So let me just maybe clean this up a little bit more, because if you recall, our design is going to be carrying forward in next levels. So we want to make sure it's nice and clean and tidy so that we can start from a good place for the next level. Let me just clean up real fast. Okay, I think that's a little tidier, and that should give us a good starting point if we need to use this schematic later on. And given how much extra space there is here, I've got a feeling we're going to be coming back to this. Alright, next level is the instruction decoder. The circuit you built in the registers level can copy values between registers, while the arithmetic engine can do different operations on two inputs, but you need to be able to do both in the same circuit. To do this, build a decoder which will decide which mode our computer is in based on the 2 bits that we haven't used yet. To distinguish between the instructions of 4 different kinds, the 2 highest bits will be used to determine which mode we are in as follows: immediate, calculate, copy, and condition. And here the multiple color circle means any value. Determine the mode we are in from the input, then send high to the correct output. Looks like this is probably immediate, calculation, copy, or condition, based on the instruction. And there should just be 2 bits. Let's start with a byte splitter, because we know we're going to have to access these 2 values right here. And we could, if we want to save logic gates, we could try and implement some logic ourselves, but it might actually be easier to just use a decoder here, because based on these values, it will select between the different inputs that we need. And that honestly will make it really easy for us, at least to solve this level. In real life, you would want to use as few logic gates as possible to save on cost, but for the sake of just figuring out the logic, let's do that first. If we go back to our level log and see what values we need here, if they're both low, it should pick immediate. So I can hook that up to the immediate output. If we have low then high, then we want calculate. So that's this one, because here's calculation. Then this is copy, which should be the third. If we have high low, should be copy. And then finally, high high should be condition. So I think that is decoding and choosing the right operation. Let's run this and see. All right, our circuit has been saved to the component factory. There's our instruction decoder. Okay, that's gonna do it for this episode. Thanks for tuning in. It's starting to get pretty complicated here. The next level we're gonna do is calculations and conditions, and we're getting so close to having a working computer. Don't forget, if you like the webcam, if you think the audio sounded better, let me know down in the comments. If you enjoyed the video, a like would go a long way towards helping the algorithm know that this content is cool. So thanks for tuning in once again. I'll see you next time.